Welcome to the January 2019 meeting of the Houston.net Users Group. You're welcome to join us in person for pizza, prizes, and networking on the second Thursday of every month. Our meetings are hosted by Improving Houston in their office at 10111 Richmond Avenue, just inside the Beltway in Houston's West Chase District. You can check us out for meeting notifications at HDNUG.org, on Facebook, or on LinkedIn. Unfortunately, we didn't have a sponsor this month, but due to the outstanding support that we've received from our community over the years, we're still able to provide great prizes and have an awesome meeting. If you're interested in sponsoring HDNUG, please let us know. And now, our featured speaker, Mark Reynolds, presenting Introduction to Azure Machine Learning.
All right. Good evening. I'm Mark Reynolds, currently in transition, although hopefully maybe some of you guys can help me with that tonight. And last year I decided to get into this Azure Machine Learning. I've given a couple of presentations. Some of you may have already seen this one, but I'm going to hold it over one more year. So before we get too far into it, I want to give you a definition of machine learning. Forgive me while I read this PowerPoint. It will serve for impact. A computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task T as measured by P improves with E.
Okay. That actually makes sense. Yeah.
It makes sense. I like to say it gets better with time.
And experience.
And so
Because without the experience, it won't get better with time.
that's right. And
It's kind of like people.
But then how do you measure better?
well,
Well, that's performance.
you can measure performance as being better, yes. But what is performance? Performance on the racetrack is a different performance than on Wall Street.
You have to have a reference.
I'm sorry?
You have to have a reference.
You do have to have the reference, huh?
Reference is P.
No.
Is it?
No, that's the
Reference is
performance
a-
measure is P.
Yeah, yeah.
P0 is your reference.
Well, your reference comes into is part of it.
It could be any number of things.
That's right.
It could be recognizing apples in a picture.
That's right. And oh my gosh, I knew I forgot something. How many of you guys have seen the, is it a bagel or is it a chihuahua picture? Oh, wow. Okay, we will digress soon, but not immediately. Okay, so back in 2017, 2018, when I was doing some of these talks, I discovered the big buzzword then was big data and machine learning, prescriptive analytics. Somebody said blockchain and somebody else said no Bitcoin. Over the course of 2017, 2018, that morphed a little bit. Big data, yeah, you still hear about it, but not as a big technology everybody wants to know. They just say, yeah, we have to deal with data lakes. IoT and cloud, of course, were coming way into vogue last year. So this year, I've got 4 things so far that are buzzwords. Cognition, and a little selfless plug. I also have a presentation I'm getting ready with Azure Cognitive Services. Blockchain. How many of you guys have actually played with blockchain at this point? 1,
I've read about
2,
it.
3, okay.
I've read about it. I haven't dug into it.
Yeah, I've gone to a couple or 3 presentations by IBM and some other people, and all of them are extremely elementary and disappointing. IoT, I prefer to work in the realm of IIoT, the Industrial Internet of Things. I used to say I really don't care if my refrigerator and my toaster talk to each other while I'm away, but I realized that my bed is actually on the internet, and I have a water heater already picked out, so maybe I do care. And then, of course, machine learning, which is what we're dealing with today. Let me digress for a moment and talk about the changing computer paradigm. Years ago, empirical was where everything was at. That was observations, descriptive, formulaic. It is best known from Isaac Newton kind of a perspective. Einstein came along, he had hypotheses and investigations, and in fact that formed the basis for science fairs, which kids today are still tormented with. Computational, John McCarthy, data exploration and e-science. Jim Gray from Microsoft, he wrote a paper where IT meets science. These 4 different paradigms have evolved. The first one took thousands of years, hundreds, tens, and now we're into just years. And in fact, the data exploration that I was discussing back during the 2017 is really already beginning to go away from us. Today, the idea of cognition, I think that's going to be the big driver through 2019. Analytics applied. Look at it. There's 4 types of analytics. Some of you have heard them till you're tired of them. Some of you haven't heard them quite like this. Descriptive, diagnostic, predictive, and prescriptive. If you work your way through it, you're saying what happened, why did it happen, what can we expect is going to happen, and how can we make sure it won't happen. Think of it as document and
Could that
file.
also be, what can we do to ensure that it does happen?
Yes, both sides, yes, absolutely. All the way from the documenting up to the processing and analyzing. Now this follows a pedagogy that you can read in the internet. You'll see data, information, knowledge, wisdom. Other places you'll see the understanding added. I could spend 30 minutes on this whole concept, but the problem I found with that chain, data, information, knowledge, understanding, wisdom, it missed something, and that was the application of that knowledge that you have gained. And again, this is the year of cognition. Moving into the machine learning ideas. I used to maintain that artificial intelligence would never be achieved because once it was achieved, it would be found to be nothing more than an algorithm. A few years ago, a mayor was elected here in Houston because he was going to apply AI to the traffic system. Well, I don't think he improved it much, but in the end, it was an algorithm. How many of you know the story of the Denver airport? They built a new airport in Denver, and it was modern, state-of-the-art. This was back in the 90s, I think. And this airport, the baggage handling was going to use AI, which at the time was basically fuzzy logic. And yeah, you want your baggage handled by a system that's fuzzy. Anyway, apparently that was a bad idea. The software, the AI system for the baggage handling caused the airport to be late. It was either 9 or 18 months, but either way, a major airport was delayed opening because AI had screwed up the baggage handling. They eventually went in there and just put basic PLCs everywhere, which if you think about it, it's about all that baggage handling needs to be anyway. Well, so there it is, my thought that AI, once achieved, would be nothing more than an algorithm. But that did not allow for the machine learning. As I look at how the computers have progressed over the last decade, 24/7 monitoring systems, control rooms, they are in existence everywhere now. A decade ago, they were just starting. Predictive analytics, of course, we just discussed that a moment ago, is the earlier stages. Data mining. What was it, 3, 4, 5 years ago? Data mining was the buzzword of that year. But only recently has the idea of machine learning come in, and the machine learning is that interjection between data mining and AI. So it becomes that algorithm that I said AI must be. And over the last few months, we have discovered that AI is actually on the cusp of occurring. Now, we're not going to go to AI, we're staying with machine learning in here. There are 4 types of machine learning, and I think I know the answer. How many of you guys have seen those 4 types before? Okay. I would really be disappointed if I was being way too elementary in this presentation.
No different than people, right?
Yeah. 4 types, yes. Unsupervised learning. That's where you say, hey, here's a whole bunch of data, tell me something useful. How many of you guys understand drilling operations? Have actually been on a rig? Just a couple?
Yeah.
Okay. Well, they think it was Shell, but don't quote me on that. Gave a whole stack of data to a company and says, tell us something, help us figure out why or how to improve our rate of penetration, how fast you're drilling. So they took all of this data and came back $1 million later and said, well, we discovered that every 90 feet, your ROP drops to 0. You can always tell who's been on a rig. For the rest of you, you take a 90-foot strand of pipe, you bring it up, or you insert it, you drill down, you stop. You bring the unit up to the top, you get another 90 foot, you screw it all in and go again. Every 90 feet, the ROP stops. That is unsupervised learning. Tell me something, show me something about ROP. So that is the 90-foot discovery. That is not the only piece of idiocy that machine learning has discovered. At Southwestern, we paid a company, now I won't say the name here, but paid them a lot of money to go out and discover something useful. They came back and discovered that the amount of casing required in a well is directly proportional to the total depth of the well.
Fascinating.
Fascinating.
Probably also how many 90-foot stops it'll have.
That's right, yeah. Yeah, how many 90-foot stops? Now, it did give another useful piece of information. You know, in horizontal drilling, you go down 3,000, 4,000, or 5,000 feet, and you turn that pipe horizontally. Well, they discovered that when you enter the curve, the torque goes up.
Oh, duh.
Okay, so there's the problem with unsupervised learning. Supervised learning. You can play with the data so much that you have over-tweaked it. And you may make a set of data so well tweaked that you can derive anything you want to derive from it. In the real world, you don't have that. The data needs vetting, not extreme over-vetting. Semi-supervised learning, watch out for your rabbit holes. You'll say, look here, look there, and it will start chasing something. An example, if you've ever done a Excel chart of a 3rd, 4th, 5th power equation and trying to find the maximums, it may traverse and find a local maximum, but not the maximum. That's the kind of rabbit hole you can end up chasing here. And finally, reinforcement learning, that's where you go in there and you're saying, yes, okay, you're doing good, computer, let's work at this, and you keep playing with it, interacting too heavily, too closely, and it becomes brittle. Brittle because as soon as you give it a new set of data, the whole thing cracks. Now, you will not, I'll come back to that in a moment. Okay, there are a couple of screens on the machine learning process. I don't want to get overly dramatic here, overly detailed, I should say, but you're going to bring your data in. You have to pre-process it. You take that prepared data. Now, until you've iterated here, this is where you can get overly supervised. Then you start applying algorithms, and there are a lot of algorithms, and the first one you apply will not necessarily be it. You find a candidate model, you iterate until it's what you want it to be. You come up with that chosen model, Now you're ready for your application. Look at it a different way. You go in, you look at your historical data. Let me pause here for a moment. When I was first started writing software, I was using DBase, and we had files which were tables, and we had records which were rows, and we had fields which were columns. And you'll still hear me often talking about fields or rows or records, but they were all synonymous. In the machine learning world, you do not have columns, you have features. Now, let's face it, it's still a column. When you're talking to a machine learning guy, just substitute the word in your mind, you will be fine. You take it after you worked on your features. I'll come back to what you have to do with that in a moment. You want to split the databases into typically 2 or 3 sections. You want to take the lion's share, 70, 80% of the database, not less than 50. Use it for training. That means that you need to have some diversity of the rows that you're bringing in. Random sampling, maybe you want to try it 2 or 3 times, but you're training against the lion's share. If you have 2 sets of data, then the second set is used for validation. So you might have a 70-30 split there. If you're hiring a third party, then you might do a 50, 25, 25. He'll do 50% for training, 25% for validation, and you'll save back 25% for testing him. In any event, with any type of machine learning, just about, you will be splitting the databases. You build the models, you go through your process, everything is iterative, wash, rinse, repeat, eventually come out with the answers. Now I'm going to show you how to come up with some models and results in Azure in a moment. What I'm not going to spend any time on is then using a service to connect to it and bring it back. You can play with Azure all day long, and it's free, and they love for you to do it. You start connecting to it with the service. Well, first off, you're talking about what kind of service do you want and how do you want to do it, and there's charging you for it. So we're just going to say this group of people should be able to write a service. Okay. Common algorithms for machine learning. You've got to think about what are you trying to solve. In a moment, we're going to look at mushrooms. We're going to look at the whole stack of mushrooms. Are they poisonous or are they not? You hope that one of those 2 decisions you don't get wrong. Preferably, you like to get them all right. In this particular scenario, though, you only have a limited number of species of mushrooms and a limited number of descriptors of those mushrooms. And you could, if there's 1,000 species, you could write 1,000 if statements and get a correct answer in every case. So when we're talking about this classification, categorization, often we will sample the entire database because it's a limited set of data anyway. If you want to know, is this guy a good credit risk or not? Now you get into a case of how sure am I? So in the first case, you're dealing with trees and if statements. In the second case, you're probably getting into the thinking ideas, and I'll get to that in a moment. There is also an area called, not regression, clustering. You've all seen at various times clusters of points. Typically, there'll be a green cluster and a red cluster and a blue cluster. That's exactly what clustering is, and the machine learning will let you find clusters of points. We will briefly touch that. So within the machine learning are common items, decision trees, typically for 2 or a limited number of answers, Neural networks, we'll talk more about that in a minute, what it is, but it's trying to emulate the way the brain is processing data. Clustering, we talked about. Bayesian probabilistic ideas, and it really works just the same way. And that's enough of that. We could spend the next 3 hours in here. This is available online. Just simply look for an Azure Machine Learning cheat sheet. We're not going to try to read it in here. It is useful in that it is Microsoft Azure. That makes it useful, right? The regression methods, the classification methods, the multi-class classifications, that's where, is it A or is it B? That's a 2 class. Is it a red or blue or yellow? That would be multi-class. And then clustering doesn't have a lot to show us to keep us interested. We're doing fine on time, aren't we? Another picture that I found today, and only to show you that there's a lot of cheat sheet type things you can find. We're not going to try to read either of those here tonight. So, getting closer to the actual demo that you're hoping for. Write this down. If you write nothing else down, studio.azureml.net. This is not the kind of a URL Microsoft would normally be known to use. .net is, everything is Microsoft.com. What is this AzureML.net? And when you get in, it is free. I have been playing with this for over a year. They've not once asked me for any money, which is good. You'll sign in. I sign in using my normal Microsoft Live email. Once you get in there, you have a control panel, a dashboard, and this that you see here is all of those projects I set up. Now, one of the joys about no longer working at Southwestern Energy is I no longer have access to all these things that I had set up, because that was set up with my SWIN account. So you will see a little less polish tonight when we get to it. The R language does interface. We're not going there tonight. Time series is its own beast, because unlike here's all of your inputs, what is my answer? With time series, you're saying, here is what has occurred, what's next? When we get in here in a little while, I tell you now, only to tell you again later, you spend most of your time in the experiments. Most of the time, we're hitting that new button down there at the bottom. That's how you create a new experiment or upload data. As you move between your experiments or your projects that you're working on, it will show you the map of the project that you're doing. We're going to talk all about this map in a few minutes, but as you arrow down through here, you get more and more information. I'm not going to actually upload a data set tonight, because that's a good way to get stuck in a presentation, start trying to upload something. I have already uploaded a data set, and it is exactly as simple as I propose that it is. You click new, you click data set, you browse to it, and you put names on it. I guess the CSV with header is the only important thing of this data that we're using tonight. Having uploaded your data set, now once you've trained your model, if you want to take a event send it up, have it evaluated, bring it back down. That's fine. We're talking about training the model here. This is my mushroom data set. It basically has, is it edible, poisonous or edible? What's all these descriptions about it. I don't really care what all of those things mean. I think I can figure out what a color is. But we got cap color, gill color, and veil color. For the purpose of what we're doing tonight, this is a table of data, and that first column is what we're striving to find an answer to. Would you agree that success, that the best we can hope for is that if it says it's poisonous, it is, and if it says it's edible, it is? That's what we would hope. When we get started, we're going to find a screen that looks like that. It is so tempting. You're going to want to click something over here, drag it, and drop it in the slot. They're having fun with you. That is a graphic background that after you drop the first little thing on this workspace, that graphic background goes away. But you will still try to drop the first one in the rectangle. Too fast here. The idea here would be, here's your data, here's your split or your training, depending on what you're doing. Here's your experiment, here's your evaluation. That's kind of the flow that we're going to see. Take the data, run a process against it, see how good it worked. In the case of the mushrooms, let's assume that if you have a mushroom with a red cap, let's make that poisonous, okay? So no matter what else is about this mushroom, if that cap is red, it's poisonous. Well, then you would have a tree, presumably, that the very first thing is the cap red? And then you'd branch off. Well, with the database that we have, the system went and found several tree logics. Every one of them gave a 100% accurate result, but every one of them was based on where did you start your process. Now, when I took this as a course back, 2003, as part of my master's, we actually had to go in there and find which feature was the most likely to provide something useful to segregate it out. It didn't have to be a final answer, but segregate it.
Divide and conquer.
And how do you divide it? Upon which one do you divide it? And that's basically primary component analysis. And there are actually tools in here that will let you do PCA. Or for our purposes here, we're going to come up and find all of those things, and it'll find the examples here. I'm doing it like this so I can tell you what the concept is, what we're going to do, and then we're going to do it. And then depending on the amount of time we have left, we'll talk about the different types of analysis. Okay, here then is my mushrooms. A two-class boosted decision tree. I think that was decision forest. Basically, if you think about a forest of stuff and you're trying to choose your path through it, that's what this algorithm is trying to find. I'm also running a two-class neural network. Let us stop for just a moment and talk about neural networks. The idea is that you have any number of inputs, and each input is given a certain level of credibility to the next stage. An excellent example that I thought of on the way here, my son and I were talking about ways and how that you can tag and say, there's a policeman up here. And when more people say there's a policeman there, it begins to have credibility. Well, I would say that there is an extra element where it becomes machine learning, because until then, it's voting. How many people say there's a cop here? How many of them say there's not a cop here? Well, what if you have twice as many people saying there's not a cop here, but 90% of those people are known to lie to you? So here you're taking the credibility of the source. You're taking multiple inputs. You don't know if there's a cop there. Waze sure doesn't know, but they know that they've got 10 people that are typically correct saying yes, and 15 people that are known to mess with you that are saying no. You would vote with the 10, and that would be the application of weighting and looking at just a piece of the data and adding it together.
Confidence factor.
Confidence factor, excellent. Okay, so as we take the data will be sent into a training mode. Now this here is really the traffic cop saying this is how you're going to train. This is the module that trains, then it runs it and scores it. In this scenario, that one set of data is being used for training and being used to score it. We have a limited set of data, might as well use all of it. If we were talking about credit card, is it a good or a bad charge? We would probably split this data, some for training, some for checking. Okay, in our mushroom example, we're going to find that true positive rate and false positive rate. This is a perfect score. It basically ignore that line because effectively everything is correct.
That's based on the question, is it poisonous?
Correct. Based on that.
A false positive would be bad.
Very much so, yes.
A false negative wouldn't be so bad.
It would not be so bad. And when you're, when you get
Is
first,
this poisonous, then a false positive is okay, but a false negative is bad, right?
Not in every case.
Did you say,
Is this poisonous?
If it's
if
poisonous,
it's
a false
poisonous,
negative would
and
be
the answer
bad.
is yes, and the answer is wrong,
That would be a false positive.
that'd be a false positive. So false positive isn't so bad, a false negative would be bad. Right.
is that what we decided?
Yeah.
Okay.
Yeah, if we say it's not poisonous, then you try it.
I think it's very easy. All mushrooms are poisonous.
Yeah.
But
Best way to
if
go.
the question is
I
this
won't eat 'em.
mushroom
I don't eat
okay?
them either.
Exactly.
Then a false positive would be bad.
You know, highly dubious of tomatoes.
False positive, false negative, yeah. But you guys understand regardless of the semantics here, and I really don't care about the semantics. Okay, a multi-class neural network. A multi-class is where you don't have it is or is not poisonous. In this case, you have is it red or blue, is it green? Now there's two ways to train a vision system. I want to digress for a moment. And it was really neat when I saw this. Somebody took a red ball and a blue box, and he taught his system, said, okay, look at this and learn. And then he brought out red balls and blue boxes, and I think the other way around, the red boxes and blue balls, and basically categorized all those right every time until he brought a green one out. And it kind of broke. It wasn't red, it wasn't blue. It tried to call it blue, but it didn't really fit. And then he brought out a triangle. It doesn't know what to do with the triangle now. That is a way of saying, here is the correct answer. Always reference this. It turns out that in most vision, it is possibly as good or better to show it what it's not. These are balls. These are not balls. And let it learn from that. Now, we're not going to get into vision so much, so I'll just throw that out tonight. The neural network, let's see. We'll come back to that. In this case, we found, is it edible? It thinks it's edible. We had 100%. Over here, now this was with a decision tree. Over here with the neural network, if it is edible, 80% of the time it said it's edible. Well, there's your false negatives, I guess. But it's down here where it's poisonous, and 3.4% of the time it told you go ahead and eat it. The big point here, there are a lot of machine learning algorithms. Some of them will work for a particular problem and some will not. Okay, we're going to come back to that because we have a demo coming up. Oh, the k-means clustering. I talked about where you have the red dots, blue dots, and green dots showing a clustering of information. Basically, think of it as a simple x squared plus y squared square root, the distance between points. The clustering is going to look at how to find clusters such that everybody in that cluster is close to the center. So it has to both find clusters that can have centers and then find who is in that radius around that center. We're not going to spend a lot of time with that either. We will not finish everything tonight, no matter what. Tic-tac-toe. This one, we may spend some time. There's kind of a corny way of doing k-means clustering, and it basically, your grid is completely full of X's and O's. Was there a winner? And there could be more than one winner, and that's not even addressed in this scenario. Poker hands, it looked at all of the types of winning poker hands, and it tried to learn how to identify, not how to place bets, not which cards to draw, just saying, if you see these hands, based on the experience, how does it rank as far as winning? And that's tremendously more difficult than you think. Okay, in fact, here we go. When we get to this guy, one pair, 56% of the time, it said is one pair. Don't let me think here. Now I'm confused about this chart here. Oh, there's. I was looking for all the rest of the numbers. So it says it's nothing 40% of the time. Well, that was a pretty bad algorithm there, even for pairs. Let's scoot down here to 4 of a kind. 80% of the time it thought it was a single pair. Here's another algorithm. I love that name, confusion matrix. Again, the results were not exactly stellar. What you want is all of those diagonals to be 100%. The time series example, we're not even going to approach it. This is really just to say there's a lot here to learn. Simple neural regression, regression being, finding the equation. We're not going to get to this tonight either. So, somebody said they wanted a demo. What could go wrong? Okay. Now, when you, I told you a little while ago, you sign in, you get over to this dashboard. That was the dashboard. I hit new down there at the bottom, and now I'm going to start asking what kinds, and it gives you a lot of training examples. It even gives you some vision examples down there at the bottom. There's your credit card processing, all those frauds. there's some good looking neural networks. Let's look here for just a moment. I do not want to go too far into this, but everybody wants to know what a neural network is. Here, everything on the left is inputs, data inputs going into these neurons. Each of those neurons multiplies or applies a weighting and then distributes that weighted number onto the next level, and so on. In simple neural net systems, you've got 1 or 2 hidden layers. When you hear deep learning, there may be 100 layers. And we're not going to have time to get too far into that tonight. Okay. Let's see here. You see, we got binary classifications there. There's letter recognition. That one's kind of fun because it gives you parameters. Now, it doesn't. You have to take numbers that you don't know what the letter is, and these are telling you how much of the space that you're looking at is dark. How much of the top, the bottom. It assigns quantifiers for all of the physical appearances of a letter, except it doesn't actually say which letter it is. So that example there is trying to do letter recognition. Now the neat thing is that if you use the Azure Cognitive Services, you just simply send a picture and get the answer. It's kind of cool how that works. K means clustering. Let's see here. There's a primary component of analysis picture. I think there's some more letters. And then we're up at the top. To build an experiment, I'm going to start with a simple blank experiment. There's our fictitious background that you are supposed to drop stuff into. And I told you that we had some mushrooms. So you get it over here, and that's what I told you. You just want to drop it on there, but it just doesn't matter.
Does the mushroom data come with the studio?
Yes, and it's also downloadable. Yeah, this is pretty much an off-the-shelf, the mushroom data.
So all this example, the data source are available, right?
In fact, let me just follow with what you're asking there. Under samples is stuff you get from Microsoft right there. And the mushrooms are in there somewhere. I found them before. It's kind of funny, that course that I took back in 2003, we used this same mushroom data set. So I dug through all my stuff. I found this data set. I uploaded the data set, and I looked, and at that particular time, it was like the second or third entry along here in the samples. Now, they may have taken it since it's not there now, but yeah, and it was exactly the same table. Okay, this is our mushrooms. If it's not there, you can find it and download it. Every one of these little boxes, these processes, and let me reemphasize, that box there is a CSV file that I uploaded. I went new, I went data set, I went from local file, I browsed, and this is what I'm not going to do because this is a kiss of death, because look, there it is. Yeah, let's upload my 2013 financials. You get the idea. So that is just the CSV data. You click on these little dots on the bottom and you will get to visualize whatever the result of that item was. And in this case, we're visualizing all of the features. Features are synonymous with what?
Field.
Columns, yes. So here's the features. Is it edible? What's the cap, the surface, the color, bruises, yada, yada. You can actually see a visualization of the different columns. It's not particularly useful. That is the output. Now, we're going to take this thing through the process, and most of the clicks that you'll be doing is down here in the machine learning. When we're done, we're going to evaluate. Now, the process is to train it, to score it, to initialize it, to train it, to score it, and evaluate it. You see, just like they say there, initialize it, train it, score it, and evaluate it. You see the, so
I'm looking.
they say evaluate, initialize, score, train. Totally random order. You should initialize it, train it, score it, and evaluate it. I'm going to drop the evaluation down here just so I can leave it there. And eventually we will see the results down here. And I'm going to back into this deliberately. And we're going to, there's different ways to score these things. I'm not doing anything fancy, using the nice basic, how do we score it? Now I'm going to be doing a couple of methods. So the idea is going to be that we're going to evaluate those two methods. And see which one's best. Now you're not going to get any answer down here because it doesn't know what it's evaluating yet. Well, so what would you be scoring? You would be scoring a trained system. So we're going to have it, since we're going to look at two different methods here. We will train our.
How do you know how to trust the score?
Because it's going to show you all the reasons to trust it. And we will get there in a minute. You're going to score it by taking the model that it created and evaluating it against your data. So here's where it gets, remember I told you that you'd normally do 50% for training and 50% for scoring. When you're talking about a system that has a fixed number of rows and you're not looking at it being able to make a decision in the future, you don't ask it to say, can you identify a red triangle in the future based on what you know? You only have a limited number and you've given them all the scenarios for all of them. So now the only thing left to do here is to tell it how the model's going to work. We're doing a classification.
You don't have to have two models.
No, good point. Maybe I should have come in with the second one later. We're going to look at these mushrooms from two directions.
Could you have N modules?
Yeah, but then that evaluate model bottom kind of gets more complicated because it only takes two inputs. If you're starting to do something like that, what you're doing is iterating through different scenarios, finding one or two that you like.
No.
Because you would, I mean, look at all that. What is that? About a dozen different classification approaches. And this one's probably about as simple as it gets.
What's the scoring based on straight through to the score?
I'll answer that in just a moment after I add this particular guy here. And whoops. That's a good question, and come here. Now, let me go ahead and draw the line here. I really should have just done one of these and then come back. when we're training this model, what is it we want to know? Is it edible? So that is our criteria. When we compare it to this other system, what do we want to know? Is it edible? Okay. When you have a mouse and you try to click it and drag it, it changes the scale. When you have a trackpad, I don't guess you can change the scale. So we will just,
You have to use 2 fingers.
No, use plus minus under the button.
So it depends on the trackpad.
well okay. We don't have to do that. Let me go down here. I'm going to tell it to run. If you've already,
You click on that little plus and minus where it says 1 to 1, and there's your scale. It's down at the very bottom below the little square that says mini map.
Bottom left.
thank you.
That's another way to do it.
Yeah. I much prefer getting in front of a group of people and then letting them tell me how to run my software. Okay. Notice it says run selected. After you've created the thing the first time, you can make a tweak and then run a single box. I deliberately wanted this whole thing to run while we talk about it. And it will take it a moment. Now this is the free Azure ML. You can actually get it to run faster if you pay it. So, wow. Wow. I've never had it run that fast before.
Maybe he already knows the answer.
I guess it must. Okay, so here is our data, our table. Here is the description of a 2-class decision forest. And you can visualize what it's doing. I don't care to go into great depth, but it's telling how the constraints for this tree are defined. It is not the trained model. It is instructions for training the model. Same thing over here. This trained model is going to output, visualize it. There are our trees, and you can change which one you want it to use. Whatever floats your boat. And if you don't care, you can zoom in. It will tell you which feature it's selecting on each one of those. It's your standard flow chart. Okay, scoring the model. What we have here coming out, here is the original table. Over here on the end, the first column is still edible, P, E, E, P for the first 4. Over here on the end, it says, well, we decided that it was P, E, E, and P, and this is the probabilities. Now, this is a 2-class, so probability of 1 is this class, probability of 0 is not this class or the other one. Basically, there's what it found in the entire table. And as you then eventually, there is your decision forest approach. And was expecting to see something else. Nevertheless. Okay, so the story of what is it doing here? There's our data, 1,000 or 900 and some odd rows, being fed into this module that does the training. This is the constraint, which is a decision forest. Build me a model. That is the model, the model algorithm. That is the tree. Take that tree, run it against the data, and see how close we came out
See how close to what?
to what you wanted. You want that when it is edible, you want it to say edible. This is the thing that is trying to evaluate that answer.
Okay.
How accurate are you?
I mean, while you're training, you know the answers, so you can grade it.
That's right. Now, in the case of a limited number of rows, two-class system, you hope in building a tree that you get the correct answer every time, even if you need 1,000 if statements to get the job done. When we're talking about a credit assessment, it's not nearly as easy. If you're trying to decide, is it red or is it orange? It's not as easy. You're looking at variations, gradients.
So how does this model find its way into production?
Into production, once you have completed the model, and I have not done it, I have seen it done. You save that model, you put it as a service. That's when they start charging you. And then you call the service like you would call a service. I've seen it done, I've not actually done it. It's kind of, this exercise left to the reader.
There's no free tier?
Not for the service, because they know that if you're calling it with a service, now, there may be part of the $200 a month that you can get from them, but yeah, if you're calling it with a service, then you're no longer learning machine language, you are using machine learning.
You're basically publishing it to be used.
Exactly. That's exactly the correct word. I should have said it myself. Publishing it for use.
And by publishing it, you're charging whoever uses it a fee for using it.
Yes. Okay, let's go to the next one here. And I'm not going to build this one from scratch because I'm lazy.
There's no, I'm only playing.
This is the only, I'm only playing.
This is that credit assessment. And we're not going to so much go through,
This is building widgets
yeah.
for production.
Now, I know it's hard to read, but you don't have to read it to understand what you're looking at here. We brought in some data. We have split the data. And we can click on that and make our decisions. 75% for training and 25% for evaluating. We can give it a random seed. But the idea is that 3/4 of the data becomes trainable data, 1/4 otherwise. You hope that you can train it. If you train it with a good assortment of data, then you should come close to being able to evaluate it and score well against the holdout.
So why the split?
Because if you take all of the data and train it against that, you have now developed a system that works for that piece of data, that set of data. It may not work for any other data set in the world. So the more data you have, the better you can train it. But 50 to 75% limit so that the rest can be the scorekeeper.
And you have like three layers of splits.
3 layers what?
3 layers of splits.
That's right. Let's get through here. Okay, so, wow. Let's make this big enough where you can read some of it. This one is an off-the-shelf set of data. Split the data. It said 80%, but we know it's 75%. Validation, okay. So that data here appears to, remember I told you a large share for training, a small share for validation, and a small share for your bosses to see if you did it right. I think that's what we're seeing here. We are doing several splits. The primary component analysis, I'm not going to go into it, basically saying which of the features matter the most. And there is a topic on these features that we really got to get to in a moment. And then it comes out. And just trust me, I could have set this up for a full day class. We could have gone into all of this stuff, but we're not going to get through with it anyway. Not today. Okay, the tic-tac-toe. I tried that a couple of times, had varying levels of success. Remember I told you that we had a set of data, come here, where every cell has an X or an O in it. That's not realistic, for one thing. Every one of them positive. There's actually, of the 958 rows, about 40% of them are failure to win. The others are something won. Going through there, looking through your decision forest, your training. Now, I did not tie them together in evaluation here because the k-means clustering gives you a more complex answer that you don't just evaluate against a 2 class. The final result here, and I'm going quickly because there is something I got to get to here. There it did pretty good at figuring out if it's a winner or not. Again, 958 if statements could tell me that. Okay. When I first tried this project, I was still working at Southwestern, and I said, okay, let's take 1,000 wells and let us look at those 1,000 wells and see if I can find some simple metrics to tell me what the EUR is, the estimated ultimate recovery. After all, the total amount of gas you get out of the ground is how much money you made on that well. Well, it turned out to be a lot more difficult than I thought, because I figured, hey, I would take fields, I'd take counties, pads, I would put in there when they were drilled, I would put how much they've actually produced. Nice and simple. Life is good. Well, with a neural network, it will take all of those features. It will look at the pad name and apply a confidence factor or a component to that. It'll look at the lat and the long and say, can we graph this thing out geographically? And it will try to take a big multivariate equation, bring all of those items together, and have a nice little formula to tell you what the expected ultimate recovery is. I couldn't get the thing to work, couldn't get it to work, I finally whittled that data set down to, I said, I finally whittled it down to what is the average daily production? Well, that's the total production divided by the number of days, right? I mean, 8th grade stuff should be able to do that. I put those 3 columns in, and it couldn't give me a regression to solve it. The problem was, it was taking the features provided, the total gas produced, total number of days, tried to affect a weighting factor, add those weighting factors together and give me the result. Well, that's not what you do. You take one number and divide it by the other. And in fact, it couldn't even figure out, well, multiply this number by that number. It needed the reciprocal. So all that's to say, when you are dealing with real world, complicated scenario, your features are not clean as they are. You may need to convert your lat longs into the sine and cosine of the lat long and make those a new column of features. The machine learning is not going to say, well, if we take the cosine of that column and multiply it by e to that column. So feature generation. If you have 5 features, you could easily have 100 columns of features. Every kind of the tangent, logarithm, this times that. And feature generation is a major critical part of the machine learning. Once you have, yes, sir.
So this is where, when you pay your mechanic on the car, they know what bolt to turn. This is where the person who is good at this knows what feature to generate.
And that brings up another good point, because there are, now I'm on a soapbox now, this is my soapbox. We have dealt for a long time, every one of us in this room has dealt with being a software developer trying to relate to the user. And those of us that have dealt in the world of physics where processes, that is difficult because the users always have their own vernacular. And the developers are always trying to say, well, this is obviously a .NET solution, and they're over here saying, it's not so obviously a .NET solution, you don't even know how the thing works. Your subject matter expert, your developer, and now we've had a new guy jump in here called the data scientist. We now have 3 people, and all 3 of them have their own lingo and do not understand the other people. One of that group of people will be able to fit somewhat in the middle and talk to all of them. Somebody will rise to the occasion most of the time. Coming back to the thing, that subject matter expert can tell you that every 90 feet the progress stops. The subject matter expert can tell you that the deeper you go, the heavier the mud, creating a greater hydrostatic pressure. Therefore, your calculation of hydrostatic pressure is a variable of depth. Your data scientist knows that the hydrostatic pressure and something else are your basic features. All of these guys have to work together. And back to some of the things I showed a few minutes ago, the feature generation, remember I showed that chart? Said I'd come back to it. Feature generation is a crucial step to the machine learning. Everything I've shown you live has just been how to take features and calculate results.
Feature generation is basically, as I view it, the analytical part of the relationships of different pieces of features, different features.
Yes.
Combining features in various and interesting ways to see what kind of correlations you can get.
I mean, these hints to models,
Sorry?
I mean, we're giving hints to the model.
We are. And more importantly, we're taking known models of the real world and applying to get the features that the model can use.
So it can automate.
Yes. You can take all the numbers that are produced during a drilling operation and feed them into the machine learning, and maybe if you give it a powerful enough engine, enough time, it will find useful stuff for you. Or you can use feature generation and get the thing started. And that, to me, my experience has been one of the biggest differentiators between the companies that are selling machine learning solutions. Okay.
And that is,
I'm sorry?
I'm just, you know.
Their ability to do feature generation.
no short-term memory.
I'm sorry, what was that?
I said I have no short-term memory.
What we're talking about?
Okay.
Yeah, but it gets worse.
Regression algorithms. You're based, you did this in 8th grade, y equals mx plus b, that is a regression. You start doing multiple powers, second order, third order, exponential regression. It's all still regression. It's all part of the tools you have in the Azure Machine Learning. Instance-based, and you're looking at the nearest neighbor. This is kind of boring, actually.
So how do you know which algorithm to which model?
There's a whole bunch of these. Okay, let's see. Decision tree, okay, we spent some time there. I want to stay here. It's all if logics. It's all based on the features that you're dealing with. Bayesian. For those of you that hadn't done much probability, if the probability of something happening is 70% or something else happening 30%, and you turn that around and say, okay, given that this has happened, what's the probability it came out of this box or that box? In other words, okay, let me start over. Here's a box that you get. A red is 80%, a blue 20%. Here's another box, probability of red 50%, yellow 50%. When you turn the Bayesian math around, if you have a yellow, you know what box it came out of. If you have a red, you have a probability of which box it came out of. And this is not a probability class. Clustering, we've talked about that 2 or 3 times. Association, if A and B, then C. The neural networks. One of the things that really helped me understand it finally, after a couple of years, was the idea of back propagation and initialization. Seems simple, but I did not get it at first. Deep learning, that's neural networks, very deep, typically about 100. There's no set rule. Let's see. I am moving
I like
quickly.
the names of some of these, like Bayesian Belief Network.
Oh, here it is. Is it a bagel or is it a chihuahua?
Muffin.
A muffin or a chihuahua? I didn't think I got that in here tonight. That is a problem for vision systems.
Some of those could be really funny looking chihuahuas too.
Some of them could be chocolate chip cookies.
If you Google muffin or chihuahua, you'll find a whole lot of other, one of them's a chicken or a something else.
Yeah.
A chicken or a cat. Okay, here's the letters. And this would be a reasonable set of letters to train and try to evaluate against. I mean, you think,
Is that an A at the end of the C's?
It looks like it, but
it
it's a
does,
C.
doesn't it?
But it's a C.
It is a C. Okay,
They're
there's a
claiming
gap
it,
there.
they're
Yeah.
claiming it's a C.
I've actually done some of this.
Yeah.
Because I work with computer-aided design, and when we were working on taking hand drawings and turning them into CAD drawings.
Yeah.
We had to scan them and vectors are easy. Lines are easy, curves
Yeah.
are easy even.
Yeah, right,
But
okay.
lettering could be very difficult.
A lot of companies are really into creating data lakes out of written records, PDFs and charts. And they have lots of fun with that.
Data lakes,
I'm sorry?
data, L-A-K-E.
Data lake, L-A-K-E, like drive a boat on it.
Yeah.
One of the things that Intergraph was, I was working with, with Intergraph equipment, one of the things they were working on was association too. If you see a C in a certain set of characters, then it's
Yes.
a C and not an A.
And like with the ways, you may have a very few number of people say there's a cop, but we trust those people. Okay, this is the attributes applied. So those are the letters, I believe. Yeah, and then those are the attributes across. So the T has those attributes, and that's the names of those attributes. And that's not our purpose here. If you're in a vision effort, it is. Oh, that's just how you, and this is actually one of the examples in the Azure Studio. And the confusion matrix. So if it isn't A, 85% of the time it thinks it's an A. That's not yet effective, not yet useful. Ah.
Huh. A few of those are hard to decide.
They are very much. Oh, there's the chicken and the cat. No, that's the, what is that? That's
Popcorn and ice
cat.
cream or kitten. You know, the one of the things that strikes me about some of that stuff, right, is you can look at that and you can see how it would be hard for a computer, but we don't have a problem picking that stuff
I know
out.
it. Well, some
Right.
of the time we do.
Most of the time, we don't have a problem. And I think one of the things that
Now,
that
there's a
it
couple of
highlights
those.
is, particularly when I'm talking to like high school kids who are just getting into it, right? Having them recognize that there are things that we do without even thinking.
Yeah, the human is still a better processor.
Well, we've
Yes.
had years of training.
Yes.
Well, it's just a matter of time.
Yes, but we said, but we now have computers winning chess matches. And we now have computers winning chess matches.
But still though, come on guys, a computer cannot appreciate that.
And we could teach the computer to appreciate that. And that's the
And-
thing.
and-
And then why do that? That's that's really.
Now that has
This kind of goes back to.
feature,
Yeah,
it
yeah.
might be easier.
You mentioned high school kids. One of my best friend's son is now no longer high school age, he used to be. And he would sit there and play this game called Hot Dogs or Legs. And it was literally a game on his phone where he was identifying whether he thought it was hot dogs or legs. And I'm convinced that was training some kind of network to be able to distinguish something. for some
That
reason.
is very likely possible too. Okay, let's get through
But
this.
if you Google hot dogs and legs, that one's a tough one.
Okay, let's see here. IoT, I don't know why I put this here. I think I just needed that one. Okay, finally, the Jurassic Park screen. It's not, how can we, but what's the objective, or in some cases, should we? We've been marching all the way through here. Data, information, knowledge, understanding, wisdom, application, and cognition for 2019. Machine learning gone awry. This is an actual example from Amazon a few years ago. Making of a fly, you can read about it. This making of a fly is like a $6 pamphlet. And Boarding Book, which is a fairly reputable people, they said we could charge 3% more than other people for the same item. And these guys said, well, we don't have reputation, we don't have lots of stars, but we could normally charge 98% of somebody else and still get the business. Those two companies started bidding against each other for that $6 pamphlet. It came up to $23 million plus Shipping.
We actually did that too for, when I was working back in United, we had this ticket thing, and we were doing the same exact thing.
Yeah.
There was one ticket to Hawaii, it was like $6 million or something. I'm like, yeah, they can buy like an island, 60 million, something like that.
Yes, and they're using the same basic logic there.
Well, computer-based trading is much like this.
I'm sorry?
Computer-based trading on the stock market.
Yeah.
Wasn't there a similar thing that happened where Amazon ended up paying people to take Xbox Ones?
Oh, our host, Devlin Niles, got in on this thing. Amazon came up with this thing. They want, in some cases, to give you a rebate. And in other cases, they want to give you a discount. So with this new, this is a year or so ago, this new Xbox or Game Master or whatever thing came out, $600, they screwed up. They gave you 100% rebate and a 100% discount. They paid you to take these things. So he actually got himself a brand new game something with a rebate.
Is this why when something maybe go out of stock on Amazon for a bottle of shampoo, the price goes up to $1,500? Okay,
I don't know.
crazy.
I do know that in the case of the game device, that Amazon lost $60,000, wrote a paper, and just let everybody keep them.
By the way, there was an easy fix. Like, we had the same problem back in United. We just, all we had to do with the code was like put a cap.
Yeah. Okay.
It's like one line of code.
You're right.
Fixed.
But as far as simple fixes, how many of you guys, you got to have a little bit of the same color hair as me. Some years ago, mid 80s, the entire long distance system in New York City went down. You remember that story? Anybody?
I have the same color hair.
Basically, New York City, you could not place a long distance call. Well, what had happened, they figured out, was these control units, switching stations, one of them would get overloaded and do a reboot. When it came up after reboot,
It was overloaded again.
these other stations deluged it. And somehow all of these things were in queue. It blasted them when it came back up and overloaded another station. All during the day, these stations were popping up and off and on. Well, a cousin went to work for AT&T up in New Jersey. I asked him, I said, did they ever figure out what happened? He says, yes. I said, what was it? He says, promise you won't tell. So somebody forgot to put a break in a switch statement. Okay, let's see here. Those are the important URLs. You can get to this. I currently have it on LinkedIn through SlideShare. I've got a couple of updates, but nothing greatly significant for you. And I can go back. I just want to draw attention to the fact that in the list of companies I've worked for, one of them is called TVD.
What he's saying is he's available for hire.
That's what he said, yes.
Thank you.
And with that, Jay, I have managed to go 3 minutes over.
Can you go to the next slide?
Other questions?
We've been doing questions all the way through it.
Oh, I wanted to allow you to get through it. From what I've gathered, studying this a little bit, one of the challenges is actually diagnosing the machine learning system. In other words, it's a bit of a black box as far as diagnostics are concerned.
Actually, that is,
Or I'll use an old phrase, debugging.
yeah. Actually, user acceptance is what a big issue is. If we go in there with that mushroom database and I show you the tree, and you as a subject matter expert can read that tree, and probably will, what did it come up with as this great solution? And look through it and think about every angle there. But when you throw a neural network in there, you can only say, well, statistically, it's going to be fine this much of the time. And it's okay if Netflix or Pandora plays a song you don't like. If they got it wrong, you thumb down it, you go on, nobody cares. It's okay if your browser ad window shows you something you don't really care about, nobody cares. If it makes a wrong decision out on a gas station, gas well pad, and instead of shutting it down, it wide opens.
Right.
Now you have this problem. Energy companies do not like to be on the headlines. Headlines are bad. So, yeah, the joke is, you made a headline. Well, telling the production manager, this system here will optimize your production station. It will learn what works, and it will adjust the choke and everything else. And all you have to do is sit back and rake in the profits. It's much more important to him not to make a headline. Much more important than increasing profits. As important as that is. So yes, that there is to get the acceptance, you've got to convince these people that are very smart, but often don't trust computers so well. Skeptical, it doesn't even begin to explain it, to get them to buy into your answer. And for that reason, I've always advocated against too much automation in the process. For one thing, if we're talking about production optimization techniques on the pad site, you want to take data in over time, you want to run the analysis, you want to find an answer and deploy the algorithm to the wellhead. You do not want the wellhead performing machine learning. That should be done back home.
Thank you for joining us for the January 2019 meeting of the Houston.net Users Group. Our meetings are on the second Thursday of every month and are held at the Improving Houston office at 10111 Richmond Avenue. Join us at 6:30 p.m. as we kick things off with pizza and prizes. So if you happen to be in Houston on any second Thursday, we'd love for you to join us.